Let's continue our discussion. In the previous video, we have discussed rules to determine significant figures in measured values. Now we are going to discuss rules for arithmetic operations with significant figures. So the key concept is the calculated values should not contain more significant figures than the measured values which are being used in the calculation. What does this sentence mean? Let's take an analogy and then we can understand. Let's say we have a chain of four links, and the strength of these links means the tension they can tolerate. We can say this link has strength of 12 Newton, this link has, let's say, 10 Newton, this link has 8 Newton, and again this has 10 Newton. And now if we are going to ask how much tension we can apply on this chain before it breaks, so we have to find out the smallest uh, or weakest link, and the weakest link is 8 Newton here. So if we are going to apply a tension greater than 8 Newton, this will break. So no matter we have link of strength of 12 Newton or 10 Newton, but the chain has overall strength of 8 Newton, which is the weakest point. In the same way, no matter if we have several measured values and those measured values have several number of significant figures. So no matter what is the highest or other number of significant figures, we are going to concentrate on the weakest link there, means the lowest number of significant figure, and that should be reflected in the final result. For example, let's say we have measured two lengths, L1, let's say 2.55 centimeter, and L2, let's say 2.1 centimeter, and now we are going to add these two lengths and we want to know what is the final length. So we can add in the way 2.65, but here we have to be careful about this thing, because in the second value here, this is the uncertain digit. So if this is the uncertain digit in the second measured value, then we are going to add this to this 5, and then after adding this we have the uncertainty here. So this is uncertain digit in final result, so no need to keep the digits beyond this. This is what we are going to say. The calculated value should not contain more significant figures than the measured values. So in this way, we are going to retain the number of significant figures after arithmetic operations. Okay, let's discuss a little more about it. If we are doing multiplication or division, the final result should retain lowest number of significant figures, as we have discussed earlier. So let's take an example, then it will be more obvious. Let's say we have measured length of a rectangle. Let's say it comes 10.5 centimeter, and its breadth is something 2.5 centimeter. And now we are going to say what is area. Area should be L into B, and then we have 10.5 into 2.5 centimeter square. Okay, after calculation we will get something here. Let's calculate it. Then this should be, I think, 26.25, if I'm not wrong, centimeter square. Again, we have to be careful about this, that the lowest number of significant figure in any measured value is here 2. This value has 3 significant figures. This value has 2 significant figures. So in the final result, we should have 2 significant figures only. In this way, we have to keep up to here only. That should be 26 centimeters square, and we have to drop these values. Okay, let's continue our discussion. In case of addition or subtraction, we have already seen an example here. So what do we need to do? We need to keep the digit up to lowest place after decimal. So let's take an example, then it will be obvious. Suppose we have measured one value 42.5 centimeter, and another value 2.5 centimeter, and then we are adding these two. It should be 45 centimeter. Okay, but one thing we should be careful about, that we are, if we are not mentioning this decimal place in the final result, it's a 45.0 centimeter. If we are writing in this way, actually we are losing an information, a piece of information you can say, and that is about the precision of the instrument used in the measurement. So if we are writing only 45 centimeter, then we can't say that the instrument we have used has precision of 0.1 centimeter. This information will be retained only when we are keeping this 0 after decimal. So in this way, in addition or subtraction, we have to keep the lowest decimal place. Let's take another example, 42.55 centimeter, let's say, and another one, 40.5 centimeter. Oh, let's make it easy, 2.5 centimeter. Okay, so what is happening here? It is 45.05 centimeter. Okay, now is this value reported correctly here or not? So first thing, we have to find out the weakest link, and the weakest link is here. This value has only two significant figures, means this value is up to one decimal place, up to one place after decimal, and this has two places. So the final result should be in accordance with this value. So this thing is not going to be mentioned. So the final result is again 45.0 centimeter. Okay, let's continue our discussion. Look, we are truncating these things here. We are going to look what is happening, not here, maybe in this case. Okay, here we have truncated the things. These digits we have dropped. So there are certain rules. How can we round off or estimate these things? So let's discuss about that. Okay, rounding off the uncertain digits. So what are the rules? Let's say we have to round off a number that is 2.35725. Okay, so if we have to round off this number up to two certain digits, up to two significant figures, then we have to keep the things up to here. If we have to round off this value up to four significant figures, then we have to keep up to here, and then we have to drop these two things. So there are some rules. How can we drop the things or the uncertain digits? So let's continue one by one. Okay, if the digit chosen means up to where we are going to drop, let's say if we are going to keep up to five significant figures, let's say first thing we have to keep up to five significant figures. So 2.3572, and then we have to drop from this digit onwards. So there are no digits onwards, so we have to drop this 5 here. Now how can we drop this? We can, this is our chosen digit. So if the chosen digit is greater than 5, let's say our chosen digit is something else. If it is greater than 5, then we have to add 1 in the last digit, which we are going to retain. If the chosen digit is less than 5, then we need not to add anything. We can simply drop that digit onwards. And if the chosen digit is equal to 5, then we have to observe the last digit which we are going to retain in the value. So if that last digit is odd, then we have to add 1 to that digit, and if the last digit is even, then we need nothing to do. We can drop simply. We have to keep the digit as it is. So in this case, based on this discussion, what we need to do, if we have to keep up to 5 significant figures, we can do 2.357, and this digit is, look, our chosen digit is 5. Then we have to check the digit which we are going to return up to is odd or even. This is even, so we need not to do anything to it, just we can write it as it is. Okay, suppose we are going to keep up to 4 significant figures only, let's say 2 4. Then our fusion digit is this one. From here we have to plug it. So this is 2 and this is less than 5, so we can drop simply without changing this digit. Okay, let's go to 3 significant figures. Okay, 3 significant figures. Then our fusion digit is 7. This is our fusion digit, and we have to keep up to 1 to 3 significant figures. So this is greater than 5. So if we are truncating from here, we have to drop this 7, but this is greater than 5, then we have to add 1 in this last digit which we are going to retain here, then it will become 6. So in the same way, okay, let's do the last discussion. Up to 2 significant figures, let's say, if we are going to keep up to 2 significant figures only. Okay, let me make it more clear. Yes, so to keep up to 2 significant figures, that is 2.3, but we have to take care of this digit. This is 5, and if the chosen digit is 5, then we have to check the digit which we are going to retain is odd or even. And here 3, this digit is odd, then we have to do one thing, we have to add 1 to this 3 and then it will become 4. So this way we can estimate or round off. So I hope from this single example you can get idea of all different scenarios. Yeah. Let's take one more example very quick. So we have 4.572 and we have to round off up to 2 significant figures. Okay, so up to 2 significant figures we have to keep up to here. Then our chosen digit is this. From here we are going to truncate. So this is greater than 5, then we have to add 1 here, and then after rounding off it will become 4.6. Okay, okay, let's end our discussion with one more topic here, determining uncertainty and estimation in the final result. So let's take an example. Let's say we have used an instrument of list count 0.1 centimeter, and we have measured length of a rectangle 10.5 centimeter and breadth 2.5 centimeter. Okay, now this is list count 0.1 centimeter, means there may be uncertainty of 0.1 centimeter in the measurement of length, as well as the same amount of uncertainty in the measurement of breadth also. Okay. Now if we want to know relative error in the measured value of length will be delta L by L, and this thing we can write 0.1 by 10.5. And if we want to know the percentage error in length, this should be delta L by L into 100, and after calculating this thing we are going to get 0.95%. Okay, here I would like to mention one thing, that relative error depends on the measured value also. Here we have length 10.5 centimeter. Okay, with a precision of 0.1 centimeter. Now we are going to check the relative error in width. So let's move to the next slide, and then relative error in breadth. I'm writing just B here. So this will be least count divided by measured value, and I think this should be 0.1 divided by 2.5, and then percentage error in this case will be 4%. Now look, I just mentioned about this thing that the relative error or percentage error, of course, is depending on the measured value. With the same precision, we have measured two different values, length and breadth, and we can see if the measured value is large, relative error or percentage error is less compared to the measured value which is smaller, the relative error or percentage error is greater in that case. Okay, coming back to our discussion. So total percentage error will be, as we are going to calculate the area of this rectangle, so we are going to use length and breadth. So we have total percentage error, the percentage error in length here 0.95% and percentage error in breadth. So 0.95 plus 4, that will be 4.95%. Okay, this is total percentage error after calculation. We are going to find out area, that will be length into breadth. Okay, so area will be 10 point, let's check what is the value of length, is 10.5 centimeter and multiplied with 2.5 centimeter. So 10.5 into 2.5 centimeter squared. So the area will be 26.5 centimeter square. Okay, I would like to mention one more thing here. In our previous discussion of the same thing, where we were retaining the number of significant figures, I have written that, just a moment. Okay. Okay, so I have written only 26 centimeters square, keeping the things in mind that the number of significant figures in final result uh, should not be more than the number of significant figures in the measured value. Okay, and for that we have to check which measured value has the lowest number of the significant figures. So here it is 2, so we have kept only two significant figures. But while doing calculations, what we are going to do, we are going to keep one more uncertainty. Look, in significant figure, if we are writing 26 centimeter square, this is certain and this is first uncertain digit. This digit is already uncertain digit. So here what we are going to do, we are going to keep one more uncertain digit. That will increase accuracy of our, or precision of our calculation. Okay, so let's continue our discussion. So we have kept one more uncertain digit here. Okay, now this is area, and now we are going to report the error. So what is the total error? 4.95%. So if we want to know what is the 4.95% of this value, we have to do a calculation here. That will be 4.95% of this value, and if you are going to calculate this, you may find it should be something 1.3117 and maybe further. So we are not interested in all those decimal places, but this will be 1.3 after. Okay, so how can we report this area? Look, we generally report the value plus minus error or uncertainty. Okay, so the value is 26.5 plus minus uncertainty is 1.3. And now it's time to make an estimation so that we have the number of significant figures in accordance with the rules we have discussed. So we have to keep up to two significant figures only. So here we are going to drop this 5 after decimal, and here we are going to drop this thing. So this will be 26 plus minus 1, and of course it is in centimeter square. So in this way we can report the area of the uh, rectangle which we have measured. Okay, let me do a quick summary of this thing. So what we have done here, we are going to calculate the area of a rectangle, and we have measured its length and breadth. Okay, so this is length, this is breadth, and we have used an instrument which has least count of 0.1 centimeter. That is, while measuring length and breadth, we have uncertainty of 0.1 centimeter in each case. Then we have obtained relative error in length, and then we have obtained percentage error in length. Okay. In the same way, we have obtained the relative error in breadth and then percentage error. Now, we are going to use length and breadth both. So we have accumulated this percentage error here. This percentage error is going to be reflected in the area. So we have calculated this area here, and we have kept up to two uncertain digits so that our calculation will be more accurate or more precise, we can say. So, of course, accuracy and precision are two different things. We can discuss it later. So, uh, this is area. Now, we have uncertainty of 4.95%. So, we have obtained that thing in terms of value. This much is uncertainty in the area. And then we have reported the value along with uncertainty. And finally, we have make it up to two significant figures. Why we have done this? Because in our measured values, the lowest link is of two significant figures. So in the final result, we should not keep more than two significant figures. So that's all for this class. Next video, we are going to discuss about dimensional analysis. We are going to do dimensional analysis, and after that, we are going to discuss some previous year questions of your NEET exam. So that's all for today. Thank you.